Module 1.2, Factoring Polynomials and Combining Rational Expressions. These are review sections 4 through 5 in your book. Factoring polynomials and working with rational expressions now will make working with trig equations easier later. So we're going to review how to factor polynomials and how to work with rational expressions. Now, some important concepts to focus on. You need to remember and practice the usual steps for factoring polynomials. Factoring polynomials is always difficult. You just have to practice it. The more you practice, the easier it'll get. The most important thing when factoring polynomials is to check your work. You should always know whether you have the right factor or not. All you have to do is check your work, and you'll know if you were correct or not. Also, rational expressions look very complicated, but it's really the same rule as just working with fractions when you're working with numbers. The same properties apply. The same rules that we've gone over are going to apply for rational expressions. And always try to look for factoring if you can. Now and in later modules, if you can factor a problem, factor it. It will make working with the numbers and expressions a lot easier. All right, factoring polynomials. Factoring, like with numbers, is just writing a number as its product. So for example, if you have a polynomial x squared plus 1 times another polynomial x minus 2, right? You know how to multiply that out. X squared times x is x cubed. X squared times negative 2 is negative 2x squared. 1 times x is x. 1 times negative 2 is negative 2. And you know how to combine things. X cubed, negative 2x squared plus x. None of that combines. Right? So factoring is just going backwards. If you start off with x cubed minus 2x squared plus x minus 2 and can figure out how to get the factored form, then usually that will make problems easier. Okay. Here's an example. 2x squared plus 8x can be factored as 2x times x plus 4. And again, the only way you really know is to check it by multiplying it out. 2x times x is 2x squared. 2x times 4 is 8x. You can always check your work. When factoring polynomials, the first step you usually take is to look for a greatest common factor between terms, or any common factor, but usually a greatest common factor. So if you have something like 5x and 25x squared, you know that the greatest common factor, or the greatest things they have in common, is 5x. The greatest common factor is 5 of 5x and 25x squared is 5x. The usual steps for this is to find the greatest common factor and then write the terms as products. So for example, in negative 5x cubed plus 10x squared times y plus 5x, we can write negative 5x times x squared plus, instead of 10, we can write 2 times 5x times xy plus, and then here we can just write 5x times 1. If you're not used to writing it out like that, that's okay. But that shows you that the greatest common thing that they have in common, the greatest common factor, is 5x. Right? And everything else that's left over, like the x squared, the xy, and the 1, they don't have anything in common there. So the GCF here, the greatest common factor, will be 5x. after you've done that, you can factor that out. You can write that at the very front, 5x, and write down what's left over. If I take out a 5x from there, I'm left with negative x squared. And then here I'm left with 2xy plus 2xy. And here I'm left with just the plus 1. That's why it's important to write plus 1 or times 1 there so that you don't forget to write the plus 1. And again, you should always be able to check your work to see if you did it correctly. 5x times negative x squared is negative 5x cubed. 5x times 2xy is 10x squared y. 5x times 1 is 5x. So you factored it correctly. Check your work. Factoring by grouping. Sometimes if you can't factor the same thing, a greatest common factor from every term, then you might be able to factor the problem by grouping terms together. So for example, in 2x squared plus x plus y plus 2xy, the first two terms have something in common, and the last two terms have something in common, but all the terms don't have something in common. Let's see if it helps to factor by grouping. So we're going to take the first two terms and take out an x, because they have an x in common, at least an x in common. If I take out an x from 2x squared, I'm left with 2x. Plus, if I divide this x by x, I'm left with 1. Same thing for the next two terms. They have a y in common. If I were to divide out a y, I'm left with 1. Same thing here. If I were to divide out a y, I'm left with 2x. And again, you should be checking quickly just to make sure you didn't do anything silly. X times 2x is 2x squared. X times 1 is x. Y times 1 is y. Y times 2x is 2xy. So you're good so far. Now notice that these two terms, this term and that term right there, have something in common. They have a 2x plus 1 in common. So if I were to take out the 2x plus 1, I'm going to write it in parentheses and write down what I'm left with. I'm left with here the x plus, and here in this second term I'm left with just the y. Notice that I've written this expression, right, that's separated with plus signs, as an expression that's just separated with a times sign here. There's two things that are multiplying to each other. So I've factored it. And again, you should check by multiplying everything out. So in this case, factoring by grouping works, but it does not always work. But if you notice that the first two terms and the last two terms have something in common, you might try it. The most common type of factoring that we'll do in this class is factoring trinomials. In other words, factoring three terms. 1, 2, and 3. And we will, for the most part, be focusing on quadratic trinomials. So things of the form x squared, something with an x in it, and some number. So maybe like ax squared plus bx plus c. The easiest type of trinomial to factor is whenever the a is a 1, when the leading coefficient is a 1. So something like x squared plus bx plus c. If you have something like x squared plus bx plus c, you usually want to find two numbers that multiply to give you c and add to give you b. Those two numbers have to be the same. So two numbers that multiply to be c, but also add to bb. So as an example, if we're trying to factor x squared plus, let's see, 2x plus 1, because the leading coefficient is 1, it's an understood 1 there, then all we have to do is find two numbers that multiply to be 1 but add to be 2. Can you think of two numbers that multiply to be 1 and add to be 2? 1 and 1. 1 times 1 is 1. 1 plus 1 is 2. So those are the correct factors. This polynomial will factor into x plus 1 times x plus 1. But you should check it. X times x is x squared. X times 1 is x. 1 times x is another x. And 1 times 1 is 1. So after simplifying, we have x squared plus 2x there plus 1. And we checked that we got the right answer. What if the leading coefficient is not 1? So we do have something like ax squared plus bx plus 1. Plus c, sorry. Then the only real way that we can work these problems is called the guess and check method. Guess and check. Usually we can try to find factors of a and factors of c, and we can guess that our factored form has to look something like something x plus something times something x plus something else. So this is where the factors of a go here. Factors of a in front of the x squared, in front of the x. And the factors of c will be the second and the fourth number there. And how do you know if you have the correct answer? Well, you have to check. You have to check. This is why it's called guess and check method. Let's try an example. So let's try something like 2x squared minus 3x minus 2. Okay. Then we're going to write our factored form and guess what the answer could be. So the factors, what are the factors of 2? The factors of 2 are 1 and 2. So that's what's going to go in here. Either 1x or 2x, and here either 1x or 2x. So let's try 2x there and 1x there. And same thing, we're going to look at the factors of this last number. Factors of negative 2 are negative 1, negative 2, right? Positive 2, positive 1. It's the only way we can multiply two numbers to get to negative 2. Let's try positive 1 and negative 2. And how do we know if this is correct or not? We have to check by multiplying it out. 2x times x is 2x squared. X times negative 2 is negative 4x. 1 times x is x. 1 times negative 2 is negative 2. And let's combine terms now. 2x squared. Negative 4x plus x is negative 3x. And negative 2 is negative 2. So we have the same thing, and we got the right answer. Sometimes it might take you more than one attempt. Maybe you guessed it was 2x plus 1 and x plus 2. If you would have checked that, you would have seen that that is not the correct factorization. Let's try it real quick. 2x times x is 2x squared. 2x times 2 is 4x, positive 4x. 1 times x is x. 1 times 2 is 2. So notice that here we get 2x squared plus 5x plus 2, which is not the same thing as 2x squared minus 3x minus 2. So this would not have been the correct one, and you move on to the next guess. Let's try another example. Let's try to factor 2x squared plus, what should we try, 7x plus 3. Okay. Let's make a guess. Factors of 2. 1 times 2 is 2. 2 times 1 is 2. So those are only factors. So let's go ahead and write down 2x and x. What are the factors of 3? Just 1 and 3, or 3 and 1. So all we have to do is choose the right order, because this is a plus here and the plus there. We know it can't be minus 3 and minus 1 because there's no negatives up here. So we know it has to be either plus 1 here or plus 1 there. Right? Plus 3 there or plus 3 there. We just have to find the correct answer. Since there's a 7 here, a 7x, maybe you think that 2 times a 3 here needs to be what's done. So let's try that. Let's put the 3 there and let's put the plus 1 there. And this just comes with practice. And then you have to check it, and that's how you know whether you're right or not. 2x times x, 2x squared. 2x times 3 is 6x. 1 times x is another x. And 1 times 3 is 3. So once you combine like terms here, 6x and x is 7x. You notice that you got the same answer. So you guessed and checked. Okay. Whenever you're factoring, make sure you just have a scratch paper. You're going to have to try different combinations. If you get stuck on something, just ask for help. Another type of problem that we can factor is a difference of squares. That's anything that looks like something squared minus something else squared. So a squared minus b squared is how we usually write it. If we have a squared minus b squared, anything that looks like that, it will always factor to a minus b. Sorry, I'll write my a is weird. A minus b times a plus b. So as an example, a common example is usually x squared minus 4. It might not be obvious right now, but with practice you'll see things like this. This is of the form a squared minus b squared because it is x squared minus 2 squared. 4 is just 2 squared. So it's of the form something squared minus something else squared. So it's going to factor to x minus 2 times x plus 2. Just whatever is being squared is what goes there. And you should check it. You can check it. X times x times 2. So x squared is 2x. Then negative 2 times x and negative 2. Notice that the middle cancels and you're left with x squared minus 4. Another difference of squares, 25 x squared minus 16. This might not look like a difference of squares, but again, the 25 can be written as 5 squared. And the 16 can be written as 4 squared. So it's almost something squared minus something else squared. You just have to rewrite it a little bit. This 5 squared times x squared can be written as 5x squared minus 4 squared. So we do in fact have a difference of 2 squares. So 2 squares and they're being subtracted. So this will factor to be 5x minus 4 times 5x plus 4. And you should check it. Let's try one more. Can you guess what the factored form is? Yeah, it's 2x minus 3 times 2x plus 3, because 9 is just 3 squared. With practice, this will be easy. Objective 9, working with rational expressions. A rational expression is the quotient of two polynomials where the denominator is not 0. So two polynomials being divided to each other, and the denominator should not be equal to 0. So here we need a polynomial on the top, something like 5x plus 2, and polynomial on the bottom, x squared minus 1. And you just always want to make sure that the denominator, in this case x squared minus 1, does not equal 0. It can't equal 0 because you can't divide by 0. So any polynomial could be something like 2x squared plus x over any other polynomial, x plus 1. And x plus 1 can't equal 0. In this case, that would mean that x could not equal negative 1. Because if x is negative 1, here we have negative 1 plus 1, which is 0. Which brings us to the next concept. The domain of a rational expression is the set of all values where the rational expression is defined. In other words, what x values are allowed for example, in this last rational expression, the only thing that was not allowed for x was negative 1. The domain of any polynomial is all real numbers. All real numbers. And any polynomial like 5x plus 2, anything can go in for x. Or x squared minus 1, anything can go in for x. So anything from negative infinity to positive infinity. So because of that, the domain of a rational expression is also all real numbers, anything from negative infinity to positive infinity. So let's say all real numbers except where the denominator is 0. So as an example, we have x plus 2 over x minus 3. The domain is all real numbers from negative infinity, but notice that x can't be equal to 3 here, because if we have 3 for x, we have 3 minus 3, which is 0. So anything from negative infinity all the way up to 3, but not including 3, and 3 to infinity. So all real numbers except for 3 is what this says. Another example, give the domain of x plus 1 over x squared minus 1. Now you should start saying that really the question is, when is the denominator equal to 0? When is x squared minus 1 equal to 0? Well, if we solve for this, we can add 1 to both sides. This thing has two solutions, either when x is equal to negative 1 or x is equal to positive 1. Negative 1 squared is equal to 1. Positive 1 squared is equal to 1. So anything is allowed except for negative 1 and 1, because that would give you 0. So the domain, another way of writing the domain would be that all x is all real numbers, all real numbers except x cannot equal plus or minus 1. So this says all real numbers such that x is not equal to plus or minus 1. Multiplying rational expressions. Remember, this is just like numbers. When multiplying rational expressions, we multiply straight across. Straight across. Just like we would with numbers. For x squared plus 2 over 2x times x over x cubed plus 2x, we multiply straight across. You might want to put parentheses to be extra careful there. X squared plus 2 times x over 2x times x cubed plus 2x. And then actually multiply using the distributive property. X times x squared and x times 2 would give you x cubed plus 2x. Right? And here if we multiplied 2x times x cubed and 2x times 2x, you can do that. Notice also that we could cancel things out here. We could cancel out the x with this x. So that really all we have left is x squared plus 2. And here we just have to multiply the 2 times the x cubed and the 2 times the 2x to give us 2x cubed plus 4x. Right. Could do a couple things here, but we really just want to focus on the fact that when we multiply rational expressions, we multiply straight across. Straight across. To divide rational expressions, we multiply by the reciprocal. So we turn it just into a multiplication problem. Here, if we were dividing this instead, we would have x squared plus 2 over 2x. And we would just write this as times the reciprocal. So x cubed plus 2x over x. In other words, just flip it. Flip the second rational expression. And then it's the same as before. Multiply straight across. Multiply straight across. To add and subtract rational expressions, we need to have the same denominator. We can't add 2 over x plus 3 over x squared if we don't have the same number in the bottom. Okay. What we usually do is we find what we need to get the same denominator. So here, for example, we have an x and we have an x times an x here, x squared. So all we need is another x there. So we're going to multiply by x. And because we do it to the bottom, we need to do the same thing to the top, multiply by x. So really we have 2x over x squared plus 3 over x squared. And now that we have the same denominator, we can add straight across. 2x plus 3 in the numerator over x squared in the denominator. What about this next problem? It's a combination. There's lots of ways you could do this, and you'll find your own way with practice. Here we need to subtract 3x over 5 with 2, but then we also need to multiply that by 2 over x. You could either do this using the distributive property first, or you can go ahead and combine this first and then multiply. It's up to you. Before we can do anything with this though, with the inside part, we need to have the same denominator. So let's leave the 2x as it is, and let's write 3x over 5. And because we need a 5 in the bottom there, we're just going to put a 5 in the bottom there. Multiply. We're going to say this is 2 over 1, and we're going to multiply 1 times 5 to give us 5, and then we're going to do the same thing to the top. 2 times 5 to give us 10. Notice we haven't changed the problem. 10 divided by 5 is still 2. We're going to leave the 2 over x still, and we're going to subtract straight across now. 3x minus 10 over 5. And now we're going to multiply straight across. This is the same thing as saying 2 times 3x minus 10 over x times 5, or 5x. Right? And you can keep multiplying that out if you want to or need to. Pause and try the following on your own. Alright, so we need to add these two rational expressions, but we don't have the same thing in the bottom. We have n minus 2 and n plus 2, so we can't do that unless we have the same denominator. So we have an n minus 2, we need an n plus 2, so we're going to multiply by n plus 2 in the bottom and the top, plus 3. And again, we have an n plus 2, but we don't have an n minus 2, so we're going to multiply by an n minus 2 in the bottom and the top. And now we're going to multiply the top out, the numerator. 3 times n, and 3 times 2 would give us 3n plus 6, and 3n times 3 times negative 2 plus 3 times negative 2 would give us plus 3n minus 6. And because we're adding straight across and we have the same denominator, we can write that as one fraction. And now we can combine. 3n plus 3n is 6n. 6 plus negative 6 is 0, so those cancel out. So it's just 6n over n minus 2 times n plus 2. Give the domain of 18x squared plus 2x over x squared plus 9x plus 20. Again, remember that the domain of the top here is all real numbers. All real numbers. So you don't have to worry about the numerator. All real numbers. Same thing for the bottom. The domain, if it was just a polynomial, it'd be all real numbers. But because it's in the denominator, we need to ask ourselves, when is it equal to 0? When is it equal to 0? So that's what we're going to do. We're going to set the bottom, x squared plus 9x plus 20 equal to 0. And we're going to solve for that. Remember, this is a trinomial where the leading coefficient is 1. There's an understood 1 there. So all we have to do is find two numbers that multiply to be 20 and add to be 9. What two numbers multiply to be 20 and add to be 9? Well, let's think about it. 20, there's lots of ways you could do 20. 2 times 10, 4 times 5, right? 1 times 20. But which one of those adds to be 9? 4 plus 5 is equal to 9. So that's the right number. The right factor is x plus 4, x plus 5. And you should check it. Always check your work. Multiply this out to make sure that you do get x squared plus 9x plus 20. Okay. Remember, when two things multiply to each other to give you 0, one of them has to be 0. So either x plus 4 equals 0 or x plus 5 is equal to 0. And these two things have two solutions. This says that x will equal negative 4 and x will equal negative 5. So the denominator is equal to 0 when x is equal to negative 4 and when x is equal to negative 5. So that means negative 4 and negative 5 are not part of the domain. So the domain is from negative infinity to negative 5, but we're not including negative 5. And then from this U stands for union or from negative 5 to negative 4, but not including negative 4. It's open parentheses. Or from negative 4, not including negative 4, to infinity. Any of those numbers except for negative 5 and negative 4 are part of the domain. Should now be ready for Module 1.2 homework.